What do you think is stronger, an ant or an elephant? An elephant can lift more weight than an ant, but what about their strength compared to their body size? The answer might surprise you. An elephant can lift 500 kilograms, which is 10% of its body weight. An ant can only lift 1/millionth as much, but that amount is actually 50 times its body weight. Ants use their impressive strength to move food and materials to their colonies. How much can you lift? The average person, between the size of an ant and an elephant, can only lift about half of his own weight. Why is an ant so strong?
First, we need to understand a principle called the square-cube law, which Galileo came up with over 400 years ago. He observed that when an object grows in size, its volume increases faster than its area. Let's picture a cube. The area of one face on the cube is the length squared, and the volume is the length cubed, hence the square-cube law. This cube has sides that are 1 centimeter long. The area of a face on the cube is 1 square centimeter, and its volume is 1 cubic centimeter. Now this cube has sides that are twice as long. The area of its face is 4 square centimeters, but the volume is now 8 cubic centimeters. Doubling the length of the sides quadruples the area, but octuples the volume. As the object gets bigger, the ratio between its area and volume changes. There are important consequences when an object's volume grows faster than its area, because it changes the way it could interact with its surroundings.
The effects of the square-cube law can be observed in our everyday life. For example, in designing buildings. We can make small-scale models of buildings out of papier-mâché, but real houses are made of wood, brick, and metal. But why can't we just build a real house out of papier-mâché? The amount of weight that a structure can support is relative to the cross-sectional area, but the building's own weight is proportional to volume. Since the square-cube law told us that volume increases faster than area, a bigger building will weigh more but might not have enough area to support its own weight. These two towers are made of the same materials, but only the small one can support its own weight. Because of this, engineers need to use stronger materials like bricks to design real buildings that have larger dimensions. For a similar reason, an ant can carry more relative to its body weight than an elephant. And this is also the reason why monster ants do not exist. Strength is proportional to the cross-sectional area of their legs, while weight is proportional to their volume. Here you see a small ant holding its weight. If we now scale up the ant, we see that the ant's legs can no longer support its weight and it collapses. And hey look, the small ant can even bring treats back to its friends.
The square-cube law is also observed in aerodynamics, which is the science of flying and falling. You may have learned that gravity causes matter to fall towards the ground, and that gravity makes objects of any mass fall at the same speed. Why is it then that in real life some objects seem to fall faster than others? A falling object actually experiences two forces, gravity and air resistance, which is also called drag. Gravity makes the object fall faster, while drag slows it down. The force from gravity is proportional to the volume of an object, while drag is proportional to its exposed area. Remember again that when things get bigger, volume increases faster than area. If we drop these two different sized helicopters from 4 stories high, what happens? As predicted, the bigger helicopter fell faster, because the drag, which goes with area, increases more slowly than weight, which goes with volume.
Let's review what we've learned today. The square-cube law tells us that when an object grows in size, its volume increases faster than its area. We've seen how this can be applied to buildings, animals, and falling objects. Look around you. What else can you explain with the square-cube law?